The last type of example I'd like to go through is what we can classify as a mixing problem. So here we're given this scenario in which we have an 800-gallon tank that's filled with brine, which is just some kind of salt water, and it contains 300 pounds of salt. Every minute, 2 gallons of dilute brine containing 0.1 pound of salt per gallon are pumped in, and 2 gallons of the well-mixed brine are pumped out. We want to find a differential equation and initial condition satisfied by S of t, which they're describing as the salt in the tank at time t, and then solve this. So one thing that we're going to take advantage of that we've seen in an earlier example is that ds dt is yet again going to be something that we can represent as the rate in minus the rate out. I see that there's kind of, there's something being pumped in and then some of it's being pumped out. The other thing that is really important in these examples is to be cognizant of the units. So there certainly is a rate being described in here. We're told of salt per gallon in some sense. So what I want to think about is that the units of S, we're told S is measured in pounds. So that's pounds. Then because we're dealing with time being measured in minutes, ds dt units should be the pounds per minute. So when I'm setting up my rates here, they need to have these units, pounds per minute. So when I'm starting to separate this, the rate at which the salt is being pumped in, I certainly do want to notice that we have in this rate that every minute 2 gallons are being pumped in. So that's gallons per minute if I'm thinking about that rate. Those units aren't exactly what I need, so that's not enough. But what I can take advantage of is how I see in here this other kind of proportion, pounds per gallon. So if we have this rate of 2 gallons per minute, and we know that there are 0.1 pounds of salt per gallon, then that does give me the appropriate units of, I should say, 2 times 0.1 or 0.2 pounds per minute. So keeping in mind the units here is really helpful, I think, to find the appropriate rate in each case. Now, the rate out is a little bit harder. We're still seeing that 2 gallons per minute are going out. But if I have to think about, likewise, the kind of proportion of salt to gallons here, I have to use this notion of well mixed. So if we think about what that means, we know that at any given moment, there's 800 gallons in the tank because we're pumping 2 in and pumping 2 out. Well mixed means we can take all of the salt that's currently in there and mix it up in the total number of gallons. So when I think about what that means pounds per gallon, right, there are 800 gallons, and how much salt there is in there right now, that's exactly what S of t is going to represent. So multiplying, again, we see the gallons cancel, so my units are appropriately pounds per minute. But if I multiply 2 times S over 800, I could write that as S over 400. So well mixed just means we take the total amount of salt currently in there and then divide it by the total number of gallons in the tank. That's constant, the 800 there. So putting this together, now I see that ds dt can be expressed as positive 0.2 minus S over 400. That's separable. I would find it easier to write this in a way. I mean, you could just take 0.2 minus S over 400 and bring the whole thing over there. But I'll point out that maybe an easier way of writing this is to get a common denominator. Again, not required. But this way, I could just bring the 80 minus S over and leave that 1 over 400 on the right-hand side. Not required, but just a little bit cleaner. Now, when I anti-differentiate both sides, I do get a natural log of the absolute value of 80 minus S. However, We have to be careful and notice again, this minus sign means that we're going to have a negative over here. When I look at this, I'm going to then have an antiderivative of 1 over 400 will be t over 400 plus c. So I can get rid of that minus sign on the left-hand side by bringing it over to the right-hand side. I'm writing minus c as just plus c, but you could write that as minus c. This would tell me 80 minus s is equal to c e to the minus t over 400. And consequently, I could say that s is 80 minus c e to the minus t over 400, or I could write it as plus c. And this gives me my general solution. So what we can take advantage of is that we're told in the beginning that there are 300 pounds of salt at time 0. So technically, when we're asked to find the initial value problem, right, I would express the differential equation that we started with here, but I would also include s of 0 equals 300. That would be my initial value problem. And using that to solve it, right, now we can say that if I plug in 0 for t in my general solution here, I would get 80 minus c. We want that to equal 300. So that tells me that c is 80 minus 300, or negative 220. So this just means then that my final function here is going to end up being 80 plus, because I'm doing minus a negative, so plus 220 e to the minus t over 400. Maybe I'll put that in a different color. So this would be the solution to our initial value problem. Notice that over time, what we would expect to happen is we'd see a decrease because of this negative exponent. And that makes sense if you come back to the problem here, because salt is, or I should say, when we look at the concentration here, we're pumping in a dilute brine and pumping out the well-mixed solution. So we would expect that to affect the total salt concentration. And if we're starting off with a higher concentration, 300 divided by 800, then we expect that to decrease as we go through this process.